In this example, you will see how calculus is used in optimization problems. You are given a 100 cm by 200 cm piece of cardboard. You want to cut out squares in order to form a box, as shown in the diagram. Since you want to create a box having the largest possible volume, you want to ensure that the square you cut out will indeed maximize the volume of the box. The variable x is the length and width of the squares to be cut out. The parameter a is the length between the squares on the longer side of the cardboard, and the parameter b is the length between the squares on the shorter side of the cardboard. Using the variable and parameters, the length of the box is therefore 3x plus 2a. Since the length is 200 centimeters, write the corresponding equation and solve for a. Length 3x plus 2a equals 200 implies a equals 200 minus 3x divided by 2. Since a must be greater than 0, 3x must be less than 200, or x must be less than 66 2/3. The width is 2x plus b, and since this is 100 centimeters, write the corresponding equation and solve for b. Width 2x plus b equals 100 implies b equals 100 minus 2x. Since b must be greater than 0, 2x must be less than 100, or x must be less than 50. Taking both constraints together, x less than 50 and x less than 66 2/3, the x value satisfying both inequalities simultaneously is x is less than 50. Finding the constraint on the variable x is very important to assess the validity of your final answer later. In part II of this question, you now find the size of squares you should cut out to maximize the volume of the box and the maximum volume of the box. The volume of a cuboid is length multiplied by width multiplied by depth, so substitute the expressions for length, width and depth in the volume formula and simplify. So the volume is 3x cubed minus 350x squared plus 10,000x. To find the maximum volume, use the first derivative test. So, find the derivative of the volume function. dv by dt equals 9x squared minus 700x plus 10,000. Set it equal to 0 and solve. X equals 18.858. X equals 58.9197. This is where finding constraints first helps. You know already that x must be less than 50, so the second answer cannot be a solution. The only possible answer is x equals 18.9 centimeters to 3 significant figures. In order to justify that this x value will maximize the volume, use the second derivative test. The second derivative is 18x minus 700. Testing x equals 18.858 in the second derivative results in a negative value. Therefore, the volume is maximized at this x value. Substituting x equals 18.9 into the volume function results in a maximum volume of 84,200 centimeters cubed to 3 significant figures. Using your GDC will confirm your answers.